this video, we're going to learn how to draw conclusions about the convergence of a series by comparing it to another and then looking at the relative behaviors. For this first one called the direct comparison test, we're going to be utilizing the squeeze theorem like how we did in the integral test video. Imagine we have two sequences here, a of n and b of n, and suppose we know that a of n is less than b of n for all integer values of n. Then we have this inequality right here, and what I'm going to do to it is I'm going to take the infinite sum of every side, like so. And this makes perfectly good sense, because if b of n has bigger term values for every integer n, then of course, if we add bigger values, we're going to get a bigger sum. And adding 0 an infinite number of times can just be simplified to 0. Now that we know this information, we can conclude some things about the behavior of the two series. Okay, so remember how a few seconds ago we just said a of n has smaller terms than b of n for every integer n. Well, if the infinite sum of a of n diverges, then the infinite sum of b of n has to diverge because we're adding bigger numbers for every integer value. And on the reverse, if we know that the infinite sum of the bigger sequence b of n converges, then this has to converge because a of n is smaller than b of n for every integer n. And if we're adding smaller terms, of course, this has to converge as well. But notice that in these two scenarios, we started by knowing the behavior of one of the series. So that's a key element of the direct comparison test, is that you have to know the behavior of one of these series. And the idea here is by using information that you already know, you're going to compare it to something that you don't know to try and deduce things about the convergence of that series. Some good series to start with to make these comparisons is 1 over n, 1 over n squared, geometric, and p-series, just things that you can find the convergence or divergence of very easily, and you can use it to compare to something else. The second comparison we're going to talk about is called the limit comparison test, and this one is not as intuitive as the other one. The limit comparison test says if you have a sequence a of n greater than 0 and another sequence b of n also greater than 0, then if the limit as n goes to infinity of the sequence a of n over the sequence b of n is a finite positive number, then a of n and b of n either both converge or both diverge. And to know which one it is, you have to know the behavior of one of them before conducting this test. And if the limit is 0 or infinity, then the test fails. The idea behind this comparison is that if this limit is either 0 or infinity, either a of n grew way too fast to infinity or b of n grew way too fast and drove it to 0. So the two are different enough to where their behaviors are not the same. However, if this limit here is finite and positive, that means their behaviors were similar enough to where it's settled on a real value, and so we can make similar conclusions about the two series. Unlike the direct comparison test, it doesn't matter what sequence you call a of n and b of n, but it does matter that you know the behavior of one of them, just like the direct comparison test. To close the video, I'm going to do 2 examples using the direct comparison test and 2 examples using the limit comparison test. We're going to begin with the direct comparison test, and the first series we're going to find the convergence of is the infinite sum of ln n over n plus 1. A good way to go about doing these kinds of problems is seeing if you can rewrite this sequence here in a way such that more familiar sequences can come out of it. For example, I can rewrite this as ln of n times 1 over n plus 1. These two are the same thing. By doing this, we see 1 over n plus 1 appear, which we can easily find the convergence or divergence of. So I'm going to use it as my direct comparison. Now I have to determine the relationship between these two sequences. So for all n's greater than 1, ln n is greater than 1, meaning if I multiply ln of n to 1 over n plus 1, then it'll become bigger than 1 over n plus 1. So we have this inequality. Then I can take the infinite sum of both sides. We know that this is a harmonic sequence which always diverges. And we also see that the sum of this is less than the sum of this, meaning this series also has to diverge. The second series we're going to find the behavior of is 1 over n squared plus 4. Another way to solve these kinds of problems is seeing if can we just get rid of stuff to make it seem more familiar and then make the comparison with that series. For example, like this one, we have 1 over n squared plus 4, but if I just get rid of the plus 4, then we just have 1 over n squared, which we know the behavior of. So I'm going to use that as my direct comparison. Now we have to find the relationship between these two sequences. The denominator here is n squared, but the denominator here is n squared plus 4, meaning that for every number of n, the denominator of this will always be bigger than the denominator of this. And since they're both dividing 1, this is dividing 1 into more pieces, so this will be smaller than 1 over n squared. And now I'm going to take the infinite sum of both sides. And we also know that for every n, this is always less than this. So if the sum of this converges, then the sum of this also has to converge. That's how you use the direct comparison test. Now we're going to use a limit comparison test to determine if these two series are convergent. The first series that we'll be doing is 1 over n times root n squared plus 2. It really doesn't matter what you use for the limit comparison test as long as your chosen sequence is always positive, but there are a lot of things we can do to make this process a lot easier. For instance, if we neglected some terms here, how might this simplify? Well, as n grows larger and larger, this plus 2 becomes more and more negligible. So we can say that 1 over n times square root of n squared plus 2 roughly goes to 1 over n times the square root of n squared for large n, which simplifies to 1 over n squared. And look, we know the behavior of this series, so we're going to use it for the limit comparison test. And that whole process is just thinking through how might this series change as n grows to infinity. So now I've set up our limits, and all we have to do now is just evaluate it. I'm going to start by simplifying this complex fraction. But now I'm going to do something a little weird. I'm going to multiply by 1 over n over 1 over the square root of n squared. The idea here is that we're still multiplying by 1 over 1, but in this form, I can bring this inside the square root and simplify what's inside, and that makes this whole limit a lot simpler, and we can see what this tends to as n goes to infinity. And that simplifies to this, which simplifies to this, which simplifies to this. And from here, we can see that as n grows to infinity, this goes to 2 over infinity squared, which goes to 0. So this just becomes 1 over root 1, which is just 1. And since 1 is finite and positive, the behavior of this sum and this sum have to be the same. Since the sum of 1 over n squared is convergent, this series is also convergent. Now in the second one, we can do a similar process to find what we should compare to. Okay, so notice, as n grows larger and larger, this minus 2 becomes slowly negligible. And look at that, this turns into a divergent geometric series. Like so, and we can use this to our advantage with this comparison. Now I set up our limit, and I've separated this fraction again to make simplifying this complex fraction easier. And this simplifies to the limit as n goes infinity of 4 to the n minus 2 over 4 to the n. And we can further simplify this into this. And here we see that as n grows to infinity, 4 to the n goes to infinity, which makes 2 over infinity go to 0. And this is just 1, like the last limit. And since this is a positive finite number, the behavior of this and this must be the same. So since we know that this series diverges, this series must also diverge. And that's how you use the limit comparison test.